All right, so we're recording. Um, Today is March 23rd, and we'll take a look here at what our schedule is like for today. So this is our plan for today. We're going to be going into chapter 24. If it's okay with you all, then I'd like to also take a moment to make some comments about some of the homework problems. Notice that the homework problems are from chapter 23, so though we're moving forwards, I'd like to also take a moment to look back at some of the things that we've learned and help you all as you're trying to work out some of the homework problems. So the last hour was for office hours. And I will also maybe just address a few questions that I felt would be relevant based on that. So we're going to be talking about magnetic fields and forces today. And specifically, I'm going to actually do a demonstration. Can you believe it? I'm doing a demonstration over video. I happen to have enough materials around that I was able to put together something that I think you'll find interesting. And we're going to be looking at how a current carrying wire can actually produce a magnetic field. And we'll have some more discussion points on this. And then we'll also talk about how if you were a charge and you were moving near a magnetic field, you would also feel a force on you. And so we'll discuss some of those points briefly. And then looking ahead for this upcoming Wednesday, please read ahead chapter 24, sections 6 through 8. You'll see that we're going to be talking about magnetic fields exerting forces on currents. So if there's two wires that are having a current, then the question is, do they actually pull towards each other or do they repel away from each other? And then we'll also be talking about something called a dipole, which you saw before in the electrostatic case, but we'll be talking about what would happen if you put one of these dipoles into a magnetic field. And then we'll also talk a little bit about materials and just magnets and how they work. And then that'll conclude chapter 24. And of course, we have the spring break that's coming up this next week. So we just have 2 more classes, this and Wednesday, and then we'll have a break for 1 week. And coming back, we'll be diving into chapter 25. I think all of you know by now, you read the email or my email or from President Marishita this morning that all the classes will be online until the end of the semester. So I don't know how you feel about that. For me, I don't know if there's like this, you know how they have the how you feel about things, you can put the thumbs up or thumbs down, but I don't see where it is. But anyway, I think not so fun, honestly, but we're going to do the best that we can, and we'll try to have some fun in the process. And my hope is that you continue to learn and stay engaged. And so if there's some things that I can do to make it more engaging for you, something I can do to help, I'm open to suggestions, really. I've been thinking about ways to make this a more interesting experience for everybody. So please let me know, and we can take things step by step. We also have an exam coming up on April 15th. Maybe I should even start to put that on here. So we have our midterm number 3 is going to be chapters 23 through 26, and that will be April 15th. And we can talk about how should we do that? What is the best way to do that? I don't know, but I'm thinking about putting this onto Blackboard, and we'll discuss some of the procedures, how we can do this in the coming meetings. Okay. Just curious, how many of you would like for me to maybe, I don't know, go over a couple of homework problems from the chapter 23 that might be relevant to you all? Okay, one person. You can use the thumbs up, like the reactions down here, to do like thumbs up. Let me know. Okay, a few people saying thumbs up. Okay. And okay, there's definitely enough people now, as an overwhelming majority, that I say, yes, let's go ahead and do that. So, so I'm going to switch to the camera here. And I'm just going to write a few things here as we go. And I've just stored a few notes here for each problem. I'm not going to work out a homework problem necessarily, but I will sketch out a few notes that I think will be relevant. So, and I'll write down above each one which number it is that I'm talking about. So this is for problem 23.27. And this is basically addressing something that's called a voltage divider. And in a voltage divider, we usually have a battery, and we have two resistors that are in, is this a series or parallel? This is series. And so, for example, let's say that, oh, I'm sorry, this is, I'm sorry, I just realized that my notes were for the next one is for the voltage divider. This one shows, okay, sorry, let me do like this. 23.27, this is the problem where we have a battery and some resistor, and then we have two other resistors that are in parallel with each other, and it finally goes back. And the question is basically, how much current is going through this resistor here? And you might say, well, how do I approach a problem like this? Well, what we have to do is we have to reduce first this set of resistors as if it was one resistor. And you can do that by adding resistors in parallel. So 1 over R total is equal to 1 over R1 plus 1 over R. Okay, we had a little bit of a lag. Okay, let's see here. Let's just see what's going on here. Can people hear me okay? Oh, I see, I see. When I turn on the document camera and the video at the same time. Okay, so how about this? I will stop the video, and then I will share the screen with the visualizer. Hopefully that's a little bit better. Okay. So in this case here, we're going to be reducing this circuit to something where this is now just one resistor. And so we have that resistor and then our sort of reduced resistor. And now you have two resistors in series, which you can now combine as one resistor. And then I think that you know maybe how to approach it from there. So that's just a hint on how to continue with the question number 23.27. The next one that I wanted to bring up was 23.34. And this one is referring to something called a voltage divider. And so generally, if you have two resistors here, let's just say that this one is a 10 ohm and this one is a 20 ohm. Then you might say, well, okay, and let's say we have like a 30 volt battery here, right? But you can see that together there's a 30 ohms and we have 30 volts. So the total amount of current that's going through this circuit is equal to, it's V is equal to IR, so 30 volts divided by 30 ohms, we can see that we have 1 amp that's going through this circuit. So if we wanted to figure out the voltage drop across this guy here, this would be delta V is equal to I times R1. Let's just say this is R1 and this is R2. And in this case, so also if you do have your microphone on, maybe you can just mute it here, just so that people don't hear things like your, I don't know, pencil sharpener or something like that. If you do have your microphone on, would you please mind muting the microphone? Just trying to figure out how to mute. Okay, very good. All right, I'm going to mute that one here. Okay, very good. All right. Okay, going back. Let's see here. I need to go back to the sharing the screen. All right. So here in this case, if we wanted to figure out the voltage drop across this resistor here, delta V is equal to that current times the resistance. So that would be 1 amp multiplied by 10 ohms. In other words, this is a 10 volt drop across the 10 ohm resistor. And if I wanted to figure out the voltage drop across R2, we could say that this is equal to I times R2, which is going to be 1 amp times 20 ohms. And this is equal to 20 volts. So you can see that if you have two resistors, the bigger the resistor is, the more voltage drop there's going to be. So that's the basic idea, and that's something that I think will be helpful for you in problem 23.34. Let me just double check that for this next one, I have an idea of which one it is, but I need to just double check here which number it is. I think this is 23.49, which has to do with charging a battery. Let's see here, 23.49. Oh, okay, 23.61. Okay, very good. So, so in the case here for 23.61, one of the things that it's talking about is it's modeling a battery as actually having some internal resistance in it, in addition to having the battery itself. So this is kind of the picture of, okay, there's actually this battery that looks like this. You know, we can say that this is a cell, right? But actually that there's some resistance to this thing as well. And so when they're talking about charging a battery, what you're actually doing is you're connecting another battery. This is the charging battery across the actual battery. So in that case, we would have a charger, right, with a plus and a minus side, and you'd connect that to both sides of this battery. So that's the same picture here. And if you were to draw a Kirchhoff's voltage loop, let's say starting here, let's say this is the voltage of the charger, right? So voltage of the charger, if we're going around in this direction here, and let's say that the current is also in this direction, we'd have the voltage of the charger minus IR, this is the resistance here, and then we'd say minus the voltage of the battery is equal to 0 when we get back to where we started. So that's a Kirchhoff's voltage loop. And if you write that down, that loop in this kind of situation, this will help you to figure out what voltage you should choose if the current is given. I think in my case, they were saying the current should be 0.85 amps and all the other numbers were given, but they said, well, what kind of voltage should you use if you're expecting that kind of internal resistance of your battery? Okay, very good. And finally, question number 23.49. All right, okay, very good. So let's see if I can. So here, I'll just draw a picture of it. I think it's faster. So in 23.49, there's a battery and it's shown as connected to a capacitor, but there's like this switch. And so maybe the switch is here, in which case you've charged up the capacitor to the same voltage as the battery. But then they show it in a separate situation, and the switch is this way, and it's going through a resistor here. So in that case, now you have a fully charged resistor that's going to create a current that's going to go through the resistor here like this. So I just wanted to sort of highlight that. Thought that that might be a useful picture. Is what does it mean, the switch? It means that you're either charging up the capacitor, which happens mostly instantaneously if this resistor was not here. And then in the moment that the resistor is connected directly to the capacitor, then you're talking about having a current that goes straight through the resistor. Okay, so those are my comments, and I'd be happy to talk more about this with you all if you have more questions, maybe stick around after the lecture, and we can address those issues. All right, very good. I'm going to go ahead and start my video again. Please do chime in if there's any lag. I'm sorry that there's some lag. I will post this video up online later, so then you'll have a chance to watch it again in case there's something you missed. Okay, so moving along, I'd like to start with presenting an idea, and then I'm actually going to give a demonstration to sort of to accompany that. So it turns out that if we actually have a current that's going through a wire, it may not sound like an obvious thing, but it actually creates a magnetic field that goes around in a circle around this. And so the picture here shows your thumb, and so you can all kind of try this right now. If you stick your thumb up, then your fingers will actually curl around in a circle, and that tells you the direction that the magnetic field lines will point. So the magnetic field lines are similar to the electric field lines that we talked about in our electrostatics case, except now we're going to be exploring the meaning of these magnetic field lines. So this is called the right-hand rule. And before we go any further, I'm going to do a demonstration for you. Okay, I'm going to stop the video, and I'm going to share the camera. Okay, and please bear with me here as I bring my camera over to my experimental setup. Yes, this is my couch. Maybe I should have cleared my area to make it look really nice for the camera, but anyway, here we are. That's my water bottle. And we have here a wire, okay? So this is just some speaker wire that I happen to have at home, and it's connected to a battery, okay? This is kind of like, looks like a heavy duty battery, but it's just a 12-volt battery. It's a lithium ion battery. It's pretty similar to what you'd have in a laptop. And here I have a compass. It's pointed to the north right now, but you notice that I have one of these battery terminals connected to the wire, and the other one I'm about to connect here in just a moment. And so I want you to watch this here, is that when I bring this wire close by the compass, and if I connect it, oops, if I connect it here, something's going to change. So you just observed the compass deflecting when I touched the wire. So that's the demonstration there. I hope that everybody was able to see that okay. So what happened there? This compass here, looks a little weird on the screen, but this compass basically just points to the north, right? So there's this north pointing arrow, and when I had the wire going nearby this thing, then it deflected, and it pointed in the direction of the magnetic field. Does it have to be connected to a negative terminal to start? Well, so I completed the circuit basically by connecting the battery to itself. So I made a closed circuit, and so when I had a closed circuit, we were creating an electrical current. So, and it's not magic; it's it's physics. So okay, so so maybe I'm just going to share one more thing here, which is a little simulation. And maybe this helps, maybe it doesn't help. I'm not really sure. But in any case, notice that the compass, that's like the compass that I was holding in my hand, it turns to point where the South Pole is. So in other words, a North Pole points to a South Pole. And interestingly, I can also go to this electromagnet feature here, And if we have just a battery that's connected through a few loops of wire, right? It could even just be one loop of wire. It creates a magnetic field. And so that's what we did basically, is we created a magnetic field and it deflected the compass needle. Okay, so now you've had an experience, or at least the best that we can do to get close to having an experience together. And so I'll explain to you what are the rules for this here? Well, there's this thing called the right-hand rule. And the way that this will work here is that if your thumb points in the direction of the current, then the magnetic field points in the direction of your fingers. So in this case, if you're looking at the screen right now, that X means that the current is going into the page. And so that means that the magnetic field lines, they're going around in a clockwise fashion. I have to think about it every time, but yeah, they're going around in a clockwise fashion. So the magnetic field lines are clockwise circles around the wire. Okay, so that's the way that you can figure out. This is called the right-hand rule, and it turns out there's going to be more than one right-hand rule, but that's one of our right-hand rule for a current carrying wire. Sometimes also we'll be looking at loops of current, and so the way that this is drawn, obviously, it can be difficult sometimes to draw these things on a two-dimensional screen or a textbook. So this is our strategy for drawing a loop: is that if you have a loop with current going through it, let's say in the counterclockwise fashion here, imagine that you were cutting an imaginary plane through the loop. Then if you looked at it head on, you would see this circle here represents the current coming out of this imaginary plane, and the X here will represent the current going into the plane. So sometimes you'll see that we'll be talking about a loop, but all you see is what looks like a line. But this is because we're drawing it in a peculiar way here to make a point. So hopefully that helps clarify, you know, how does this work, drawing a loop of wire. So what would be the direction of a magnetic field for this loop, for this current carrying loop? So I want you to just think about this one for just a moment. And okay, I'm going to try the first of doing a breakout here. Oh, I thought I had it figured out, and okay, let me see here. Breakout. Okay, so I'm gonna create a breakout of about 14 rooms, so there'll be 2 to 3 people, and I'm gonna give you just a moment to think about, you have a loop of current, and the question is, if you have the loop of wire such that it's that the current is going towards you on the top part, and uh, it's coming away from you on the bottom part, then which direction does the magnetic field point? See if you can make use of the right-hand rule. So I'm going to go ahead and create rooms. You should be sent into a room right now, and then we'll close all the rooms in just a moment. Okay, how did that work? Did the breakout rooms work okay? I don't know. Okay, cool. Good, good, good. All right, maybe your person didn't know that you were there. Okay, well, we do the best we can. Okay. So, okay. It looks like I lost a few people, unfortunately. Let's see what's going on here. Okay, well, okay. Once you join the room, it's like a different lecture. Okay, I see, I see. You have to leave the meeting to come back. Okay. I see. I see. All right. Well, I guess that was just an experiment. Sorry if it wasn't the most convenient thing. I guess I was trying to play around with some possibilities for us to, maybe we can try it once more in a moment here. So, um, it was cool. Okay. Okay. So we'll give it one more try here in just a moment. So the idea, at least in my thinking, is we have to think about using our right hand rule. Well, maybe I'll do this one with my video here instead of the pen and paper here. So if I have a wire, now let's just imagine that there's a loop of wire and it's going around in this direction, right? So if the loop of wire is going, the current's going this way, then that means that my hand, the magnetic field lines, that my other fingers, they're going, the magnetic field is circling around this way, so it's going into the center of the circle. So now let's look around at this other side here. My hands are going around also into the circle, right? And then again, if we use my right hand rule on the bottom here, the current's going this way, so also my fingers are going around into the center. So this magnetic field should be pointed towards me in this case. So you can use the right-hand rule to figure out which direction the magnetic field lines should be pointing. So as we just discussed here, you can use the right-hand rule to show the direction of the magnetic field lines. And you can see that the dots mean arrows pointed toward you, and the X's mean magnetic field lines that are pointed away from you. I just thought it was weird because I don't have any arms anymore. Pretty weird. Um, so, um, so that's the way that you can figure out the directions of things, right-hand rule. So now another concept is a solenoid, which is just many loops of wire. And it turns out the more loops that you carry, then per some distance, then the stronger the magnetic field is going to be. And we'll explore those formulae in just a minute. Now I'm going to practice one more here. Should we try the breakout rooms one more time, or should we just do a poll? Maybe we just try a poll in this case here. So I'm going to give you a moment to try and think through this one here, and then I'm going to have a poll, which hopefully you'll see this come up on your screen. And when you think you've got the right answer, then please select which one you think is the correct answer. So the magnetic field at this point P here, which is down at the bottom, is 0. And we want to know the magnitude and the direction of the current that's in the lower wire. I'll give you a moment to work this out. Maybe I should have also added a, I'm not sure. Okay, okay. So it looks like from what I'm seeing, there's quite a few guesses right now. I'm going to give you a little bit more information, and then we'll try the poll again. So did you remember from the text that the magnetic field strength is proportional to the current, I, and it's inversely proportional to the radius. That is to say, how far away you are from the wire. So this mu naught is a constant, which is very much like that epsilon naught that we saw from before, but it's the counterpart for magnetic fields. But so now maybe you can use this formula to figure out how you would actually get these the two magnetic fields to cancel. So to give you an idea, the surface of the Earth has a very small magnetic field, even smaller, 2 orders of magnitude smaller than a refrigerator magnet. And it's also possible to go really, really strong here, like almost 1,000,000 times stronger if you use a superconducting magnet. Okay, so let's go back to this question here. And I'm going to open the poll again. And maybe with this new knowledge that we have, maybe you can figure out how to determine the sign and the magnitude of the current that's going through the lower wire using this formula. Okay, I'll go ahead and end the polling here. If you if you even just have a guess right now, you could go ahead and click it on click on your guess. Okay, so I'll share the results with you. This is like that Who Wants to Be a Millionaire if you kind of poll the audience. And so you see, it looks like the most popular answer is this 5 amps to the left. And then the next most popular, it looks like it's 2 answers which are to the right. So I certainly agree that it looks like according to this formula here, that if the magnetic field strength contribution from the lower wire is going to be the same, it probably has less current. I can see that because if the R is smaller in this case, it's only 4 centimeters away from this bottom wire, whereas it's 8 centimeters away from the top wire, there should be less current that is required in order to have the same magnitude. But if we use the right-hand rule, I'm thinking that the current that is from the top wire is basically pointed, is creating a magnetic field that's pointed into the screen, whereas from the bottom one, I should have a direction of current such that the contribution is pointed out of the screen. So I need to have the current being pointed in an opposite direction. Let's work it out on paper here. If I have the current as 10 amps going through this one here, and it's 8 centimeters away from this point here, right? So this is 8 centimeters, right? And then we have this other wire, which has some current going through it. We can say that the magnetic field contribution, if we do the right-hand rule, then the magnetic field is going into the page because of this wire. But in this case, we want to have the contribution be coming out of the page such that they can cancel each other. So let's call this one wire 1 and this one wire 2, right? So we're going to say that we want the magnetic field from wire 1 plus the magnetic field from wire 2 to be summing up to 0. So in that case, it's going to be mu naught I.
Professor?
Yes.
We can't see the screen.
I made it short.
All we see is your picture.
Okay, how about this? Is that better?
Yes.
Okay,
Thank you.
thank you for letting me know.
Yeah.
So going back, we have wire 1 is 10 amps, and we wanted to create a magnetic field that is going, it is creating a magnetic field that's going into the page at this point here, 8 centimeters away. But from wire 2, which is only 4 centimeters away, we wanted to create a magnetic field that points out of the page according to the right-hand rule. So the sum of these two vectors should be 0. So using the formula for a magnetic field, mu naught I over 2 pi R1, and we can do I1 R1, and then we'll say minus, that'll mean the opposite direction here, mu naught I2 over 2 pi R2 is going to be equal to 0. So in other words, we can set the two equal to each other. Mu naught I1 over 2 pi R1 is equal to mu naught I2 over 2 pi R2. So you notice that the 2 pi's and the mu naughts, they all cancel out, right? And what we're left with is that I2 has to be equal to R2 over R1 times I1. So if I1 was 10 amps and R2 was 4 centimeters and R1 was 8 centimeters, then we're going to have 4 over 8. Notice how I didn't worry about putting it into SI units because it was a ratio of two numbers, times 10 is going to give me 5 amps. And that is going to be pointed in the opposite direction. So we know that the current needs to be pointed this way if the current is pointed this way for the wire number 1. I'll just go back here real quick, just so you can see that. All right, very good. Okay, I'll just pause here just to see if there's any questions. Go back to the working. Can I see the work on the paper again? Yes. So we basically summed up the magnetic field, and the formula for magnetic field is mu naught I over 2 pi r. That's kind of our big starting formula there. I realize that it is a little bit fast, Eden. That's why I'm also recording, so you can replay it more slowly if you want to watch it again. If there's a specific part that you want me to address, I'm happy to do so. You set them equal to each other because the forces cancel out. Exactly. So one is creating a magnetic field that's pointed in one direction, and the other is creating a magnetic field pointed in the other direction, and they're canceling out with each other. That's exactly right. Okay. So so and is that why it's equal to 0? Yes, because these two fields are summing up to 0. That means they're canceling each other out. That's exactly right. Yeah. Okay, so then in this case, the answer to this question is 5 amps to the left. Okay, so let's treat this one here as one that I work out, just in the interest of time. We have 2 concentric loops that are lying in the same plane. One has a bigger radius, and the other one has a smaller radius. The bigger one, the smaller loop has a 3 centimeters radius and a current of 12 amps, and the bigger loop has a current of 20 amps. And we're trying to figure out that in this case, we also have a situation where the magnetic field at the center of these loops is found to be 0. So the question is, what is the radius of the bigger loop, And what can we say about the direction of current flowing in the loops? So in order to know this one, we need to know the formula for the magnetic field of a current loop. And so this is a very similar formula, but don't be confused that it's just going to be slightly different than our current in a wire, in that it's mu naught I over 2r, where r is the radius of the wire. And this magnetic field equation is telling us what's the magnetic field in the center of the loop. So I'm going to write that on my page, and then I'm going to go to the camera here. So mu naught I over 2r. And by the way, this is the magnetic field just in the center of the loop. So we have the larger loop and a smaller loop. And the smaller loop has a radius of 3 centimeters. And oh shucks, I already forgot what the numbers are. Let me take a look again here. 12 amps and then 20 amps. Okay. So this one has 12 amps going through it, and the other one is going to have 20 amps. Now I instinctively wrote it as going the opposite direction. Can you see why? Is that the 12 amps is going to contribute a magnetic field that points into the page, but the 20 amps, if we have it going around in the opposite direction, is going to contribute a magnetic field that comes out of the page such that they cancel each other out. So again, I can say that B from the inner loop plus B from the outer loop, those should sum to 0. So here we can say that mu naught I over 2r, this will be for the inner one, plus mu naught I over 2r for the outer one should be equal to 0. And if they're going in opposite directions, the current, then they should have a minus sign on them. By the way, sometimes we also write a minus sign on the current to indicate that the current's going in the opposite direction. So again, I can use here I1 over R1 is equal to I2 over R2 in this situation. And so here, we're actually trying to figure out what is R2 in this situation. Well, we can solve this equation for R2, and we can get that it's equal to I2 over I1 times R1. And so finally putting all these puzzle pieces together, we have 20 over 12 times the 3 centimeters for the inner loop. And so looks to me like there's going to have to be more current going through the outer loop in order to, sorry, the radius is going to be larger than this, and in order to cancel it, we're going to need to have more current, which is the case because it's 20 amps versus 12 amps. So in this case here, 20 divided by 12, use a calculator here. 20 divided by 12 is 1.67, and then multiplied by 3 is 5. So finally here I can see that the outer loop is going to have a radius of 5 centimeters based on this. So we're basically just calculating the magnetic field in the center, and so the magnetic field in the center is not 0 just with one loop. But if we use 2 loops and they go in opposite directions, then it should be possible to create a current such that it the 2 magnetic field contributions cancel at the center. Now that doesn't necessarily mean that the magnetic field is 0 everywhere in between the loops. It's just talking about right at that center point. Hope that addresses those issues. Okay. So this is our formula here. And another thing that I want to just note is that the magnetic field at the center, if you have a bunch of wires that are all in a big loop, the more wires you circle, then the stronger the magnetic field is. And that's basically just because you have, it would be the same as having more current going through your loop. So this is the formula that we use. And you can see here that if this is a loop of current, that at the top it's coming out of the screen towards you, and at the bottom it's going into the screen away from you, then the magnetic field lines, according to the right-hand rule, are going to be pointed to the right. And if you had another loop that was the other way around, such that it was coming out, the current was coming out at the top and going into the screen at the bottom, then that would create a magnetic field that points in the left direction. So you'd have the two opposing magnetic fields that have the possibility of canceling each other. So there's another thing called a solenoid, and in that case, we use a slightly different formula here. The strength of the magnetic field doesn't just depend on how many turns there are, but how many turns per length. And so here is the whole length of the solenoid going from one side to the other. And the more current we have, the stronger the magnetic field, but it's really about how many turns per unit length that we actually have turned. That's going to be what determines the strength of the magnetic field. Okay, now I'll just pause to see if there's any questions. And if not, I will continue on to talk about how charges are affected by magnetic fields. Okay, so if I have a charge in an electric field, you remember that it definitely responds to the electric field, right? Remember that we had like the two pieces of tape and we saw that the opposites were attracting, and we saw that the same charges, that they were repelling away from each other. But now, how do charges actually behave in a magnetic field? Can you figure out on your own quickly which of these charges are affected? And so maybe you just copy a picture of this here, and I'll do the same on my page, and indicate the direction of the magnetic force due to this magnetic field produced by this wire. So we have a wire that has some current going off to the right, and we have 4 different types of charges, and we're wondering what's the direction of the magnetic field at each charge, and what would be the direction of the force that this charge experiences. I'll give you a moment to figure that out, and then we will come back together. I hesitate to do the breakout rooms because I don't want to lose people again. Okay, so we have some different scenarios here to explore. The first one is a charge that's moving to the right. It's a positive charge. Maybe one thing to think about here is that just if, without any charges right now, if I have a current that's going off to the right, well, which way is the magnetic field above the wire? Well, if we use the right-hand rule, everywhere above the wire, on this side of things here, the magnetic field is going to be pointed out of the page, which I drew as a circle with a dot through it. This means out of the page. Whereas everywhere below this current, in the wire, we're going to have the magnetic field is going into the page. So that's our setup here. And if we think about the positive charge here, there's a rule for how we can think about a force, and that force is basically doing something called the right-hand rule for how magnetic fields interact with charges. And I think maybe it's good for me to go back to the slides here on this one. I think that I shared the slides. Let me double check. Okay, good. So the rule for this is that if you have a magnetic field that's pointed in any direction, and you have the charges not moving at all, there will be no force. If the magnetic field is pointed in the same direction as the velocity, there's also no force. But if there's any part of the magnetic field that's pointed perpendicular to the velocity, then there will be a force. So sort of the archetypal situation here is that the V and B are at 90 degrees to each other, then the force F is pointed in the perpendicular direction. So I'm going to give you a little mnemonic here, is that if you used your index finger to be V, and you used your middle finger to be magnetic field, B, and then the force, is going to become in the direction of your thumb, F. And so if you want to get really, really dorky, you can put little, you can draw with a marker on your fingernails for a day. Everyone wants to know, why did you draw those things, right? So in other words, if my index finger, oh yeah, and also I have to do this even though we're like in a chat room, but if you have your three fingers like this, I usually have my students do this in the classroom, then you can put your index finger forward, you can try it, your middle finger to the side, and your thumb up, and then you can put it up against your forehead. And now you're a 3D loser, because it doesn't matter how you look at it, you're still a loser. So, okay, maybe you can try this one on your siblings. All right, not even a chuckle. Okay, good, chuckles, good. Okay, so 3D losers. So, so the real right-hand rule is your index finger is going to be the velocity, your middle finger is going to be the magnetic field, and your thumb is going to be the force. So in other words, even if, let's say that like the velocity and the magnetic field are actually like, there's not that much angle with respect to each other, or there's maybe 90 degrees, or maybe there's a little bit, but in any case, those form a plane, and your thumb is going to be pointed out of that plane. That's the basic idea, yeah? So that's how we can determine the force on a charge. So now let's go back and use it for our particular situation. The thumb would be Z, or depends on how you define your axis. Not sure how to answer that question. Maybe this will help clarify it. So I'm going to use my right hand here, right? I know this is awful, but anyway, the right hand index finger, and sorry, my fingers are dirty because I was working in the garden, so I'm sorry about that. But my charge is my index finger pointed this way. My magnetic field, don't worry, I'm not flipping anybody the bird here, but my magnetic field is pointed out of the page. So here, I'm going to actually stand up so you can see me do this here. Here's my index finger. This is meaning velocity. Here's my middle finger here. This is meaning the B field that's pointed out of the page. Therefore, the force is pointed towards the wire. So therefore, I'm going to write that the force is pointed towards the wire in this case. Let's take a look at the other scenarios in our examples. The other one I'm going to do is the number 4, the positive charge that's going up. That was this one over here, positive charge, and it's going in this direction here. So again, here's my index finger. Here, the magnetic field is pointed into the page. So therefore, the force is actually going to be in this direction. Here's the force, okay? Now here's the catch. For the negative charges, there's 2 ways of looking about it. You can either say, I'm going to calculate everything I would for the right-hand rule and then do exactly opposite that. Or the other way you can do it is you can actually say, I'm going to use a left-hand rule. Either of those are valid approaches. But so for number 2, we have a negative charge going upwards. So using the left-hand rule, here's my index finger. Here is my magnetic field pointed out of the page. And so then the force is pointed to the left. I could have also said velocity, magnetic field, and it looks like force to the right, but it's negative, so it points in the opposite direction. So that'd be the other way to go about doing it. And then finally, for number 3, that's a case where this velocity is going here. I'll use my left-hand rule. I'll walk around to the other side here just for purposes of demonstrating. Left-hand rule says velocity is this way. Magnetic field is pointed into the page. This means that the force is pointed upwards. So hopefully that helps clarify how the forces work with these charges. So if you have a moving charge that has any part of it that's moving perpendicular to the magnetic field, then it does actually experience a force on it. That's the basic point. And so it doesn't necessarily have to be at exactly 90 degrees to the magnetic field. It can be at some angle, like these 2 pictures here are showing that it can be at some angle, but as long as it's not moving in exactly the same direction as the magnetic field, as was shown here. If it's moving in the same direction as the magnetic field points, then we don't have any force on this charge. So not moving charges, or if they're moving in the same direction as the magnetic field, no force. So also, for example, in this situation here with the wire, if you had a charge that was either moving into or out of the page at either of these places, also in that moment there would be no force on that charge. So this is the right-hand rule here. The motion is your index finger, the velocity. The middle finger is your direction of your magnetic field, and your direction of your force is F. The way that we actually calculate this is we basically multiply the charge Q times the velocity V times the magnetic field B. And if you multiply all 3 of those together, if they're perpendicular to each other, the velocity and the magnetic field, then you will you'll calculate the force. If the velocity and the magnetic field are not totally at 90 degrees with respect to each other, then you have to put in a sign of alpha, where alpha is the angle between the magnetic field and the velocity. Notice that your textbook has a slightly different convention. You can just pick one convention and stick with it. And also notice here this note especially about the right-hand rules. If the charge is negative, then the force is in the opposite direction, or use the left-hand rule. Okay, so that's just a discussion of our answers here. The direction of the forces are shown as oh, they're not shown on here, but I showed them to you. If a charged particle is moving in a region of constant magnetic field with the direction of the magnetic field perpendicular to the direction of motion, in which direction does it experience a force? Well, in this case, it actually gives rise to a circular motion. So imagine a charged particle in a constant magnetic field, and it starts off by going up and to the left here. Well, in that case, if you use this right-hand rule, you would see that the force is pointing in towards the center, which means that this velocity would start to become more to the left. And then when you're now over here, now the velocity is going to the left, now it's going to go more down because of the force of this magnetic field. And so it'll have the tendency to make the charge go around in a circle. This circular motion can be related to our physics 125. And I'm actually going to pause for a moment to just show you kind of an idea that if you have this, here's our field, right? It's all going into the page, and we have this, this charged particle that's going around in a circle with some radius here. We can say F equals ma, right? Where the a is the centripetal acceleration, right? And you probably remember from physics 125, that was v squared over r. But the force, we just decided was equal to qvb, right? So we can put these all together here and say qvb is equal to mv squared over r. So finally, putting all those together, we can actually solve for the radius here. Looks like this v cancels out with this one, and r is equal to mv over q times r. Q times b. So interestingly, the radius actually tells us something about the, it tells us something about either the strength of the magnetic field, or about the strength of the charge, or about its velocity or its mass, right? So if we knew 3 of those things, then we could actually figure out the other. So that's kind of an interesting thing. And it turns out that particle physicists actually use this piece of information to look at the tracks of particles. And you know what, I didn't plan to do this, but actually maybe I can just briefly share with you something that I think is interesting. Let me share my Google here, and I'm just going to do particle physics bubble tracks. Yeah, so I just wanted to show you this. This is pretty interesting, actually. These particles are sent through a particle chamber, and they make these tracks, which then people can actually take images of. And the radius of these tracks here actually tell physicists about what kinds of particles were involved in high energy collisions. And so this is the basic idea. There's another one that's really beautiful. And the reason why they become smaller and smaller and smaller is because as they bump into things, they become lower and lower and lower velocity. So they do end up spiraling in. But the initial arc actually tells people what kinds of charged particles they're actually dealing with. And so Travis, yes, this is the same as the cross product, but because of algebra-based physics class, then we won't be talking about the cross product in this class. How do you know the direction of the magnetic field? That is, well, for this problem, it's just given as going into the page. Okay, so that's how we can calculate the radius of curvature. So another interesting sort of application of this is that we can actually use this. We can actually use this to, let's see, to figure out what kind of ion or atom that we're using. And I actually did this for an experiment a year ago where I went to Stanford and used one of these mass spectrometers. And so we basically put a sample into a chamber, and they sent a bunch of high energy electrons onto the sample, and it caused the ions of the sample itself to come flying out, and some of them went through this slit. And they were able to figure out what kind of speed they went through, and they knew what kind of magnetic field it was. And based on which ones got through this slit, they were able to then figure out, okay, that's this radius. They were able to figure out what mass it was for those particles. So that was kind of a cool application. And this is a common thing that's used in order to figure out, to identify what kind of molecule that you're looking at. So this is kind of an example of trying to make to measure different types of molecules in using a mass spectrometer. Okay, so let's take a look at another problem here. If I had a charged particle that was going through a magnetic field, this time the magnetic field is coming out of the page towards you, right? That's the meaning of those blue dots, is it's coming out of the page. And we have an electric field that's going up. So what are the directions of the forces in this case? Well, I can see here V crossed with B. It looks like the force of the magnetic field is pointed down. But if I remember correctly, the electric field pointed up is going to have an upward force on the on the charged particle. So we're going to have these two forces in opposite directions. If the particle was going to continue moving along with the same velocity, what does that tell us about the electric fields and the magnetic fields? Well, it looks like it says that there's no net force on this charged particle. In other words, the force that's pushing upwards from the electric field and the force that's pushing downwards from the magnetic field, they're canceling each other out. So, so that's interesting. So we could actually, in that case, say, so in that case, we could say that this is my charged particle, and it's moving in this direction here. This is its speed v, it's a charge q. We're going to have a force from the electric field that's pointed up and a force from the magnetic field that's pointed down. And so in this particular case, we can say that the force of the electric field is equal to, or you could say it's equal to the minus, right? So we could say the force of the electric field minus the force of the magnetic field is equal to 0, so they're canceling each other out. So remember that the force of an electric field is Q times E, and the force of the magnetic field is QVB. So apparently it doesn't matter what the Q is actually, it only matters about what the velocity is. So in other words, sorry. So the in this case, the electric field, or the electric force here, pointed up, is going to be equal to the magnetic field. And so that can tell you that this relationship, E is equal to V times B, is the situation that we have in this case. But now, what if the velocity was twice as much? Well, now we would have the electric field would be QE. That wouldn't depend on the electric field. But the magnetic field would be now Q times 2V times B, right? So now if we plugged in for this previous condition what the electric field is in terms of the magnetic field, we could say that that's QVB. So I said that I just plugged that in for over here, minus Q times 2VB. And we'll actually see that we get an overall minus sign, right? So in other words, we're going to end up getting minus QVB. So that means that the magnetic field is going to win, and we're going to get a net force in the downward direction in this case. Okay, any questions about that? Oh yeah, and sorry, there's one last part in here. The particle with the same mass and velocity, but with a charge of 2q, well, what happens in that case? Okay, well, let's see if we can work that one out. So we have a particle, and I already forgot the point or the condition here. A charge 2q So it has a velocity of v, but it has a charge 2q, and now we're wondering what happens. Well, if we say that the force from the electric field is just equal to E times Q, and the force from the magnetic field is equal to QVB, and then according to the right-hand rule, the directions, so I'll say right-hand rule, directions, right? So this, in this case, it'll be downwards, we know that. We notice that the EQ minus QVB, that there's a Q in both of those. And so if I make the charge twice as much, well, the force from the electric field will be twice as much, but also the force from the magnetic field is also going to be twice as much. So in that case, if we just change the charge alone, we would not see any difference in the motion, and that particle would continue going along in a straight line. Okay, very good. So our next topic will be about the magnetic forces the forces that magnetic fields have on currents. And maybe I can just start my video here. Okay. I hope everybody can see me okay. And so in this case, one of the wires is going to create a magnetic field. And then the second wire is going to have charges that are going to be moving and experience a force in that magnetic field. So I'll draw that, for example, here on. So if I1 is creating a magnetic field, so remember that the right-hand rule in this case is that the magnetic field is going to be coming up out of the page on this side of the wire, but it's going to be going into the page in this wire, or on this side of the wire. But if we have another wire in this case, and this is I2, and the I2 is going in this direction, it's as if there's a bunch of positive charges that are traveling down in this direction. So now you can kind of put together the puzzle pieces here, is that if we have a bunch of charges that are moving downwards, well, that's like saying we have a charge that's moving downwards, this V is moving downwards, and it's in a magnetic field that's pointed into the page. So again, let's use the right-hand rule. If we have V crossed with B, sorry, I'm having trouble, seeing here. So if we have V in this direction here, and we cross that with B going into the page, then the force is going to be in this direction here. So that means that this wire 1, is going to have a force that's pushing it outward. And I want you to work this out for next time, but you can go through the same exercise and say, well, actually, wire 2 is going to create a magnetic field that wire 1 is in. Which way does it push wire 1? And I think you already know the answer to this because of Newton's third law, that there's an equal and opposite forces involved. So if this I1 is pushing I2, the wire I2 away, then the wire 2 should also be pushing wire 1 away with the same force. So could there be a case where, so just going back to this previous question, I just saw that one. Could there be a case where the electric field and the magnetic field point in the same direction? Yeah, definitely. But just in this example, that they were pointed in different directions, and the 2V was just given by one of the. It was part C in the problem. Okay, so so that's where we're going to leave off for today, and I'll we'll pick up here when we pick up on Wednesday, and additionally, I will stick around for a few more minutes if there are questions about homework problems or anything else that you'd like to talk about. Hope you all have a good day, and I will be trying to post this video up for the next 24 hours sometime, and I'll post a link to a YouTube video. All right. Please take care, everybody.